Today we're going to be looking at the square root property and completing the square. Before we introduce the square root property, I just want to take a look at two quick examples so you can see why the square root property is useful. So let's start by looking at problem 1a here. X squared is equal to 4. Now, we likely can solve this mentally. If you think about what numbers squared will give you 4, there are actually two solutions. The first solution, x could equal 2, because if we take 2 and square it, we'll get 4. And the second solution, x could equal -2, because if we square -2, we also get 4. If we'd like to write this in a condensed notation, we could write our answer as x is equal to plus or minus 2. Now, this problem we could likely solve mentally, but we're going to see that there's problems that aren't so easy to solve mentally. So we need other strategies to solve these types of problems. When we've seen quadratics, problems involving an x squared, the only approach that we've learned so far to solve this is factoring. So let's see if we can solve this by factoring. If we solve a quadratic by factoring, the first step is to write it in standard form. So I've just started off with the original problem, and to write this in standard form, we want to get it equal to 0. So let's go ahead and just subtract the 4, and we'll subtract 4 from the other side. And that will leave us with the standard form, x squared minus 4 is equal to 0. Now it's equal to 0, so it's in standard form. Now that it's in standard form, now we want to go ahead and factor. So notice this is the difference of two squares. X squared is a perfect square and 4 is a perfect square, and we have a subtraction sign in the middle. So we can factor this using the difference of two squares formula. And if we factor this using that formula, we can factor it as x plus 2 times x minus 2. Okay, now we can go ahead and set each factor equal to 0. And if we solve this problem on the right, we can subtract 2 from both sides, and that'll leave us with x is equal to -2. And over here, we can add 2 to both sides, and that'll leave us with x is equal to +2. So we see that factoring gave us the same solution we got mentally. Now, obviously, for this problem, solving it mentally is much quicker, but if we have a problem that's more difficult to solve mentally, factoring is a perfectly valid approach. Let's take a look at example B here. Can you mentally come up with some number that when you square it, you get 50? You might be able to, but it's definitely a lot more difficult than this problem over here. Let's see if we can solve this by factoring. To solve this by factoring, first step, we want to write it in standard form. All right, we've got it equal to 0, so we've written it in standard form. Next up, we'd like to factor. Now over here, x squared was a perfect square and 4 was a perfect square. So this was the difference of two squares. Over here, while x squared is a perfect square, 50 is not a perfect square. So this is not the difference of two squares, and there's actually no way to factor this. So this is prime, it can't be factored. So this problem demonstrates an issue. If we have a hard time solving this mentally, and if we can't solve it via factoring, how do we actually solve a problem like this? We're going to solve this exact problem on the next page. But in order to solve this exact problem on the next page, we need to introduce the square root property. The square root property says if you have a problem of the form x squared equals c, where c is any constant, or in other words, any number, the solutions for this problem will be x equals the square root of c and x equals the negative square root of c. Or a more condensed way we can write that is that x is equal to plus or minus the square root of c. And let's check to validate that this is how our two solutions above worked. So here we had a problem of the form x squared is equal to some constant or some number, and we're saying that for these types of problems, one of the solutions is the square root of that constant. Well, that means one of the solutions should be the square root of 4, or in other words, 2. That is one of the solutions. And the other solution should be the negative square root of that constant. And let's see, that would mean that the other solution would be -2, which is exactly what we got for our other solution. Now that we've learned the square root property, we're going to use the square root property to solve this exact problem on the next page. So we can solve quadratic equations involving an x squared term, using the square root property. And when we solve using the square root property, we're going to be following these steps here. Step 1, as it says here, we need to isolate the squared term. The squared term in these two problems is just the x squared. So here this x squared is our squared term, and here this x squared is our squared term. In order to isolate the squared term, or in other words, in order to isolate the x squared, you need to make sure that the x squared is the only thing on the left side of your equation. And that's the case here. Our x squared is already isolated, so I'm just going to put a check mark for step number 1. Step number 2, this is why this is called the square root property, is because in step number 2, we take the square root of both sides of the equation. So if we start with our original problem, x squared is equal to 50. Now we're supposed to take the square root of both sides. So we'll take the square root of the left and the square root of the right. Now, right here is where a very, very, very common mistake happens, and that is anytime in any math problem, if you take the square root of both sides of an equation, you need to add a plus or minus in order to obtain the positive and negative solutions. So let's add that right here. Don't forget the plus minus. And we generally put the plus or minus on the side that has the constant. So I'm going to put the plus or minus right here. If we look back at the first problem we worked through, we see that we had a positive and a negative solution. So that plus or minus is going to help us get the positive and the negative solution. Now, remember the square root and the square are inverse operations. They cancel each other out. So the square root of x squared is just x. And now we've got a radical that we need to simplify. And if you want to review how to simplify radicals, you can look back at the chapter 6.3 video. To simplify this radical, we need to find the largest perfect square that multiplies into 50, and that would be 25. So let's rewrite 50 as 25 times 2. And I'm putting 25 in red because it's a perfect square, and any perfect square now we want to write it as some quantity squared. So let's rewrite 25 as 5 squared. Now, anything underneath the radical that has a 2 for an exponent, we can pull it out of the radical. So we'll pull out the 5. And that will leave us with x is equal to plus or minus 5 square root of 2. Now there's lots of different ways we can write our final answer. We can write our final answer like this, or we can separate the positive and negative solutions and write it as x is equal to 5 square root of 2 and x is equal to negative 5 square root of 2. Or sometimes we write our final answers using solution set notation, so that would look like this. Or if you separate the answers in solution set notation, it would look like this. So these are just 4 different ways you can write your final answer. Now, notice step number 3 says check your work. If you pull out your calculator, plug in 5 square root of 2 for x and square it, and you'll see you get 50. Then plug in negative 5 square root of 2 and square it. Make sure when you're squaring negative 5 square root of 2 on your calculator, make sure to put this in parentheses and then square it, and you'll notice that you get 50. So you can use your calculator to check your answers. Let's try b together. So we could solve b perhaps mentally. You could also solve this by factoring, since this could be factored using the difference of two squares formula, but we want to practice solving using the square root property. So these are the steps we followed. Step 1, isolate the squared term. So for this problem, the squared term is x squared. So in this problem, x squared is not isolated. So we need to isolate x squared. To get x squared all by itself, we just want to add the 81 to both sides, and that'll leave us with x squared is equal to 81. So we've successfully isolated x squared. Now that we've isolated x squared, step 2, take the square root of both sides of the equation and don't forget the plus or minus. Okay, so we can start where we left off. X squared is equal to 81. And then we'll take the square root of the left side and the square root of the right side, and we'll make sure to include our plus or minus on the side that has the constant. The square root of x squared is just x, and 81 is a perfect square, and the square root of 81 is 9. So this leaves us with plus or minus 9. So we can write our answer like this, and I'm going to write the other possible ways to write our solutions as well. Let's take a look at 2 more examples. So again, we're solving using the square root property. So when we solve using the square root property, first step, isolate the squared term. So if we start off with the original given problem, the squared term in this case is the q squared. So we want to get q squared all by itself. That means we have to get rid of the 216, and we also have to get rid of the coefficient, the 3. So to isolate the q squared, let's start by subtracting 216. That'll leave us with 3q squared is equal to negative 216. Now we've almost isolated the q squared, but we have to get rid of the 3. So let's now divide both sides by 3. And this will leave us with q squared is equal to a negative 216 divided by 3 will give us a negative 72. We've accomplished step 1. We've isolated the squared term, q squared. Next step when we're using the square root property is we need to take the square root of both sides. So if we start where we left off, q squared is equal to negative 72. We'll take the square root of the left side and the square root of the right side, and anytime you take the square root of both sides of an equation, don't forget to add the plus or minus to account for the positive and the negative of solution. Now let's see, the square root of q squared just gives us q. Now if we focus on the square root of negative 72, we need to simplify this. And anytime you take the square root of a negative number, that's an imaginary number, and we like to express imaginary numbers using I. So let's work through that process. If you need extra review on that, please look back at the chapter 6.8 video. To rewrite this imaginary number using I, let's start off by rewriting negative 72 as 72 times negative 1. Now let's pull this apart into two separate radicals. Now, let's see, the square root of 72 can be simplified. We can simplify the square root of 72 by looking for the largest perfect square that multiplies into 72. And the largest perfect square that multiplies into 72 is 36. So let's rewrite 72 as 36 times 2. And I put 36 in red because it's a perfect square. Now, anytime we see the square root of negative 1 in mathematics, that's I. So anytime we see the square root of negative 1, we replace it with I. Then 36 is a perfect square, 36 is 6 squared, so I'm going to rewrite 36 as 6 squared. And then anything underneath the radical that has a 2 for an exponent, we can pull it out of the radicals. So I just pulled the 6 out of the radical, and that leaves us with q is equal to plus or minus 6 square root of 2i. And we can absolutely write our answer like this. If we prefer to write our answer using solution set notation, our answer will look like this. Let's take a look at example number 4 here. So if we're solving using the square root property, we're going to first isolate the squared term. So if this is our original problem, the squared term is the x squared, so we need to isolate x squared. And to do that, let's go ahead and divide both sides by 5. And that leaves us with x squared is equal to 32/5. Now this fraction cannot be reduced, and we don't want to convert it to a decimal, we want to leave it in fractional form. Step 2, we want to take the square root of both sides. Now this is a common mistake. A lot of people will see the instructions use the square root property, and so right away students will take the square root of both sides of the equation. Do not take the square root of both sides until you've first isolated your squared term. First isolate your square term, only then can you take the square root of both sides. Okay, so let's take the square root of the left side and the square root of the right side, and we're not going to forget to add our plus or minus. The square root of x squared leaves us with x. Now to simplify this, let's go ahead and use the quotient property of radicals, which says we can break this apart into two separate radicals. We can write this as plus or minus the square root of 32 divided by the square root of 5. Now we need to simplify this. Let's start off with the square root of 32 can be simplified. Let's find the largest perfect square that multiplies into 32, and that would be 16. So let's rewrite 32 as 16 times 2. Okay, now when we're simplifying radicals, we want to rewrite that largest perfect square as some quantity squared. So let's rewrite 16 as 4 squared. And last, let's pull the 4 out of the radical. When you pull something out of the radical like we did here, make sure to write the plus or minus first and then all of the numbers second. Now, we've simplified this square root of 32 to 4 square root of 2. Now, this still is not fully simplified because in mathematics, we never want to have radicals in the denominator. So to get rid of this radical in the denominator, we want to multiply the top and the bottom of the fraction by this radical. This is called rationalizing the denominator. We're going to get rid of the square root in the denominator. Let's see what this leaves us with. When you're multiplying, multiply any radicals together. So we'll leave the coefficient, and the square root of 2 times the square root of 5 gives us the square root of 10. And then in the denominator, the square root of 5 times the square root of 5 just gives us 5. Now we want to double check to make sure we can't simplify any further. It looks like we've simplified as much as we can. The square root of 10 cannot be simplified. There are no perfect squares that multiply into 10. And the fraction 4/5 cannot be reduced. So we've simplified as much as we can. And we can write our answer like this, or we can write our answer in solution set notation as this. Next, we're going to solve a little bit more complicated problems using the square root property. We know the first step when we're solving using the square root property is to isolate the squared term. Now, what is the squared term in this case? In previous problems, the squared term was an x squared. or a q squared. In these problems here, the squared term is a whole quantity squared. So in problem number 5, the squared term is the quantity x minus 9 squared. In problem 6, the squared term is the quantity a plus 7 squared. So for problem number 5, the squared term is already isolated. There's nothing outside of this squared term on the left side. So I'm just going to put a check mark next to step number 1. Step number 2 of the square root property is to take the square root of both sides. So if we start with the original given problem, let's take the square root of the left and the square root of the right side. And of course, we do not want to forget the plus or minus. Now, we know that the square root cancels the square. They're inverse operations, so the radical cancels the square exponent, and we're just left with x minus 9. And then the square root of 16 is 4, so we're left with plus or minus 4. Now we want to go ahead and solve for the variable. So to solve for or isolate the variable, let's add 9 to both sides. This will leave us with x is equal to, and I'm going to write this as 9 plus or minus 4. Now we can simplify this into our two separate answers. The first answer will be 9 plus 4, which will give us 13. And the second answer will be 9 minus 4, or 5. And we can write our final answer like this, or if we use the solution set notation, we can write our final answer like this. Let's take a look at problem number 6. Step 1, isolate the squared term. And the squared term in this case is the a plus 7 squared. So if we start with the original given problem, to isolate the squared term, we need to subtract 4. And if we subtract 4 from this side, we have to subtract 4 from the other side. And that will leave us with a plus 7 squared is equal to negative 24. Now we've isolated the squared term. On this side of the equation, there's nothing outside of the squared quantity. Step 2, let's take the square root of both sides. And I'm going to start by copying down exactly where we left off. And let's take the square root of the left. And then we'll take the square root of the right side, making sure to add the plus or minus. Now, the square root cancels the square, so we're just left with a plus 7. Now we want to simplify this radical. Notice anytime you have the square root of a negative number, that's an imaginary number. And we always like to write imaginary numbers using I. The first step of that process is we're going to rewrite negative 24 as 24 times negative 1. Now, let's break this apart into two separate radicals. Now, we want to simplify the square root of 24. We need to find the largest perfect square that multiplies into 24. And the largest perfect square that multiplies into 24 is 4. So let's rewrite 24 as 4 times 6. And the square root of negative 1 is equal to I. So anytime we see this square root of negative 1, we replace it with I. Okay, now 4 is a perfect square, so let's rewrite 4 as 2 squared. And now let's pull the 2 out of the radical. Notice when we pull the 2 out of the radical, we put the plus or minus first, then we'll write the 2 that we're pulling out, and then we'll write square root of 6, I. Now all we've done so far for these last 5 steps is we've just focused on this square root of negative 24 and we've simplified it to 2 square root of 6i. For a review of imaginary numbers, look back at the chapter 6.8 video. For a general review of simplifying radicals, look back at the 6.3 video. Now we're almost there, but for our final answer, we want to actually solve for the variable. We want to know what a is equal to. So to solve or isolate a, let's subtract 7 from this side, and then we'll subtract 7 from the other side. That will leave us with a is equal to. Now there's two ways you can write this right side. We can write it as plus or minus 2 square root of 6i minus 7, or we could write it as negative 7 plus or minus 2 radical 6i. Either is mathematically correct, but the most common way to write this right side is to put the negative 7 first, and then to put this big clunky plus or minus radical thing last. So we're going to put the negative 7 first, and then we'll write the plus or minus 2 square root of 6i. Now notice over here at this point, these were just whole numbers. So we could go ahead and simplify. We could take 9 plus 4 to get 13, and 9 minus 4 to get 5. Over here, we cannot simplify this any further because these are not like radicals. The negative 7 and the 2 square root of 6i are two different types of numbers. This has a radical base, and this does not. So these are not like radicals, so we cannot take the -7 and add or subtract the 2. So we stop here. Or again, if you'd like to write your answer using solution set notation, you can write your answer like this. These problems here are just extra practice problems for you to try on your own. I'll post the worked out solutions, but you can also see the final solutions here. Next, we're going to learn the process of completing the square. Now, before we learn the complete the square method, I want to briefly discuss one important thing about the square root property. So we use the square root property to solve quadratic equations. Remember, a quadratic equation will involve an x squared term. But the square root property can only be used to solve certain quadratic equations. The square root property can be used to solve quadratic equations that involve only a squared term and constants. For example, we could use the square root property to solve this quadratic equation because this quadratic equation has an x squared term and a constant. We could also use the square root property to solve this quadratic equation. Here we have a squared term, and it's okay if your squared term has a coefficient, that's just fine. And you're allowed to have constants. You can have one constant or multiple constants. We could also use the square root property to solve this quadratic equation because we have a squared term and we have a constant. And here's one last example. We could use the square root property to solve this quadratic equation because we have a squared term. And again, it's okay if your squared term has a coefficient. And we also have constants. So we can use the square root property for problems like these that involve an x squared term and a constant or multiple constants. You cannot use the square root property if your quadratic equation involves any other x's in the problem. For example, this is a quadratic equation because it involves an x squared term, and this quadratic equation has an x squared and a constant. But this quadratic equation has an additional x term, and because this quadratic equation has an additional x term, we cannot use the square root property. Here's another example of a quadratic equation. This quadratic equation involves an extra x term here, and because it has an x term, we cannot use the square root property. Here are two other examples of quadratic equations. Notice, since they have an additional x term, we cannot use the square root property. These are all examples of trinomials. Trinomials involve an x squared term, an x term, and a constant. The square root property cannot be used to solve trinomials. Now we've learned to solve trinomials by factoring. As an example, let's try to solve this trinomial here by factoring. To solve this trinomial by factoring, we need to find two numbers that multiply to give us 1, and we need those same two numbers to add to give us this coefficient here, 4. Now there are no two numbers that multiply to give us 1 and also add to give us 4. So this trinomial is prime. It cannot be factored. So if we can't use the square root property to solve this trinomial, and we also can't use factoring to solve this trinomial, we need a different method for solving. And that's what we're going to learn next. We will learn that we can use the complete the square method to solve any trinomial. So we can't use the square root property to solve trinomials. In the past, we've solved quadratic trinomials by factoring and then setting each factor equal to 0. But the question that we just asked, how do we solve quadratic trinomials that are not factorable? We can use the complete the square method. Before we go over the complete the square process, we need to understand what perfect square trinomials are, and we also need to understand some crucial properties that perfect square trinomials have. Now, these three trinomials are all perfect square trinomials. Let's try this one first. If we were to factor this normally, we need to find two numbers that multiply to give us 9, and we need those same two numbers to add to give us 6. And the two numbers that work are 3 and 3. So we can factor this trinomial as x plus 3 times x plus 3, which can be written as x plus 3 squared. So this is why we call this a perfect square trinomial, because it factors perfectly as some quantity squared. Let's factor this one as well. We need two numbers that multiply to give us 25, and those same two numbers have to add to give us negative 10. And the two numbers that work there are negative 5 and negative 5. So that means we can factor this trinomial as x minus 5 times x minus 5, or if we write that in condensed form, we can write it as x minus 5 squared. And let's factor this one as well. We need two numbers that multiply to give us 36, and those same two numbers have to add to give us 12. And the two numbers that work are 6 and 6. So that means we can factor this trinomial as x plus 6 times x plus 6, or the quantity x plus 6 squared. So these are perfect squared trinomials because they can be factored perfectly as some quantity squared. Now, any perfect square trinomial that has a coefficient of 1 on the x squared term has two special properties that we will be using in order to complete the square. The first property is if you take the middle coefficient, the coefficient that's attached to the x, which is the 6 in this case, if you take the 6, divide it by 2 and square it, let's see what that gives us. 6 divided by 2 is 3, and 3 squared gives us 9. Notice when you take the middle coefficient, divide it by 2 and square it, you always get the constant. This happens for all perfect square trinomials that have a coefficient of 1 on the x squared term. Let's check these two down below. Let's first identify the coefficient of the x term, negative 10 in this case. Now, if we take negative 10, divide it by 2 and square it, we should get 25. Let's check. Let's see, negative 10 divided by 2 gives us negative 5, and negative 5 squared gives us 25. Let's check with this trinomial now. Let's take the coefficient of the x term, 12 in this case. Let's see, if we take 12, divide it by 2 and square it, we should get 36, but let's double check. 12 divided by 2 is 6, and 6 squared gives us 36. For all perfect square trinomials that have a coefficient of 1 on the x squared term, if you take the middle coefficient, the coefficient of the x term, divide it by 2 and square it, you'll always get the constant. We're going to use this trick as we work through the complete the square process. The other important property we need to recognize, again, utilizes the coefficient of the x, which is 6 in this case. When we're factoring a perfect square trinomial, we can take this 6 again and just divide it by 2. That will tell us what this number is here when we're factoring. So 6 divided by 2 is 3, and that's the number we put here when we factor it. Let's check here. Let's take the negative 10 and divide it by 2. We get negative 5, which sure enough was this number right here in factored form. Let's check this last one. So again, let's take this special number, this 12, and if we divide it by 2, we should get this number right here. Let's see, 12 divided by 2 gives us 6, and sure enough, that's the number right here in factored form. So just as a real quick side note, this is a perfect square trinomial that has a coefficient of 1 on the x squared term. So that means if you take the 14 and divide it by 2 and square it, you'll get 49. Let's double check. 14 divided by 2 gives us 7, and 7 squared, sure enough, gives us 49. Now we're going to see how this trick is useful very shortly, but the other important property helps us factor perfect square trinomials very quickly. This is a perfect square trinomial. We know it will factor perfectly as some quantity squared, and we can put an x here. Now, to figure out what number we put right here, we just take the number 14. 14 divided by 2 gives us a positive 7. So we put a plus 7 here. So this little trick helps us to factor very quickly. This little trick, we'll see why it's useful in just a minute. Now I've typed out the steps that we're going to use when we solve by completing the square. On the next page, I have all of these exact same steps written out as well. So this is a trinomial, and we've discussed that we can't solve trinomials using the square root property. You could try to factor this, but you'll find that it's not factorable. So this is a perfect example where the completing the square process is useful. We'll be able to solve this problem by completing the square. When you solve a problem by completing the square, the first step is to write it in standard form. Standard form means we want it equal to 0. So to get this in standard form, let's add 8x to both sides. And that will leave us with x squared plus 8x minus 2 is equal to 0. This is standard form. For standard form, we want it equal to 0, and for standard form for trinomials, we put the x squared first, the x term in the middle, and the constant last. Step 2 tells us to look at a. Now, a is the coefficient of your x squared term. If the coefficient of your x squared is not 1, we're going to have to do something in step 2. If the coefficient of your x squared term is 1, then you can skip step 2. So we're going to go ahead and skip step 2 since our coefficient of our x squared term is already 1. Next step, we're going to rearrange the standard form of our equation so that it looks like this. In other words, we want to move the constant to the other side of the equal sign. So let's start with the original problem in standard form. Now we want to move the constant to the other side of the equal sign. So I'm going to add 2 to this side and then add 2 to the other side. That will leave us with x squared plus 8x is equal to 2. Then see these orange boxes right here? I'm going to add those orange boxes to our specific problem. I'm going to add an orange box here and an orange box here. The reason being is that that's going to remind us that in step number 4, we're going to be filling in these orange boxes. To start step 4, I'm just going to copy down exactly where we left off above. Now, our goal is to turn this expression on the left side into a perfect square trinomial. How do we create a perfect square trinomial? Well, we know this special property that perfect square trinomials have. If you take the coefficient of the x, divide it by 2, and square it, that'll tell you what your constant should be. So let's do just that. If we want to create a perfect square trinomial here, to figure out what our constant should be, we take the coefficient of the x, which is 8 in this case, and we take 8 divided by 2 and square it, and that will tell us what we put here in order to create a perfect square trinomial. Let's see. 8 divided by 2 is 4, and 4 squared gives us 16. So this tells us if we want to create a perfect square trinomial here, our constant has to be a positive 16. Now we know with equations, in order to maintain equality, if we add 16 to the left side, we also have to add 16 to the right side. That's why we put an orange box here as well. Now we've created a perfect square trinomial. And I'm just going to copy our perfect square trinomial into this box here. X squared plus 8x plus 16. And then I'm just going to simplify. 2 plus 16 will give us 18. And just to write our instructions up here, in step number 4, we created a perfect square trinomial by writing. We took the coefficient of the x, which is often called b. So we took b divided by 2 and squared it, and that told us what our constant should be. Now, I'm going to copy exactly where we left off down here into step number 5. So we've got our perfect square trinomial right here. Again, we know it's a perfect square trinomial because 8 divided by 2 squared gives us 16. Since this is a perfect square trinomial, it will factor as some quantity squared. And then I'm going to bring down the equal 18. Now, to factor this perfect square trinomial, we could use our traditional method, and let's do that first. We have to find 2 numbers that multiply to give us 16, and those same 2 numbers have to add to give us 8. You'll find that those 2 numbers are 4 and 4. So that means we can factor this trinomial as x plus 4 times x plus 4, or x plus 4 squared. So we can factor this perfect square trinomial using our normal techniques like we did here, or we can use the shortcut that we learned. The shortcut that we learned says that whenever you're factoring a perfect square trinomial, to figure out what number to put right here, just take the coefficient of your x and divide it by 2. So in this case, we took 6 divided by 2, and that gave us 3. So we put a 3 here. Let's try that trick on our current problem. So to start, we know that to factor this, let's put an x here. Then to figure out what we put here, let's pretend we didn't factor already over here. We again take this middle coefficient, the 8, and we just divide it by 2. Notice in step number 4, we took 8 divided by 2 and squared it. In step number 5, we don't square it. We just take 8 divided by 2, and that gives us a positive 4. So that tells us that we put a positive 4 right here. Now, I'm going to copy this exact expression over here into the box for step number 6. Okay. Now what we've done here, we started off with a trinomial. And we know that with trinomials, you cannot solve them directly using the square root property. So what we did is we took this trinomial, we went through this whole process, and now we've turned our problem into a format that can be solved using the square root property. So this is a problem just like we saw earlier on in this lesson. We've got some quantity squared is equal to a constant, so we can use the square root property here. To solve using the square root property, first step, isolate the squared term. Well, this squared term is already isolated, so then the next step is to take the square root of both sides of your equation. And what are we missing here? We're missing the plus or minus. Now, the square root cancels the squares, so we're just left with x plus 4. And then we want to simplify the square root of 18. We need to find the largest perfect square that multiplies into 18, and that's 9. So let's rewrite 18 as 9 times 2. Now 9 is a perfect square, so let's rewrite 9 as 3 squared. And let's pull the 3 out of the radical. And that leaves us with x plus 4 is equal to plus or minus 3 square root of 2. And for extra review on how we simplify radicals like we're doing here, please look back at the chapter 6.3 video. Now, whenever you're asked to solve in a math problem, you want to isolate x. You want your final answer to be x equals something. So now, last step to isolate x, let's subtract 4. And that will leave us with x is equal to. Now here, we could write our answer in two different ways. We could write our answer as plus or minus 3 square root of 2 minus 4, or we could write our answer as negative 4 plus or minus 3 square root of 2. The more common way to write this is to put the negative 4 first, and then to put this big clunky plus or minus radical piece last. So we'll put the plus or minus 3 square root of 2 last. Now again, we cannot combine the negative 4 and the 3. They are not like radicals. This 3 is attached to a radical base, and this negative 4 has no radical base. So these are not like radicals. We cannot combine them. This is our final answer. I just realized I forgot to fill in this blank right here. So for step number 5, we factor the left side of the equation, and it's going to factor as some quantity squared. So this is the process of completing the square. Now notice for this problem, if you examine our x squared term, the coefficient of x squared was a 1. So notice we could skip step 2. The next example that we'll see, the coefficient of the x squared is not 1, so we will have to do something in step 2. So here we have a trinomial, and we know we can solve trinomials by completing the square. So first step of completing the square is write your problem in standard form. So I'm going to start by just copying the original given problem. Now for standard form, we typically like to have 0 on the right, so I'm going to subtract 6x from both sides, and I'm going to add 2 to both sides. That will leave us with 3x squared minus 6x plus 2 is equal to 0. Now we've got our problem in standard form. Now I'm going to look back at the previous page for just a minute. These important properties are only true if the coefficient of the x squared is a 1. If you have a perfect square trinomial where the coefficient of the x squared term is a 1, then you can take this middle term, divide it by 2, and square it, and that'll tell you what the constant is, and you can use this little trick over here to help you factor. If you have a perfect square trinomial, but the coefficient of the square term is not 1, then these little tricks don't work. So here we see we have a trinomial, and the coefficient of the square term is not 1. So in order to be able to use our tricks, we have to fix this and make it so that the coefficient of the x squared is 1. And to do that, it says if a is not 1, divide every term by a. So I'm going to start by copying down this standard form. In order to make it so that our coefficient of our x squared is 1, look at the coefficient of your x squared and divide each and every term by that coefficient. So we'll divide this by 3, this by 3, and this by 3. If you divide the left side of your equation by 3, we should also divide the right side of our equation by 3. This will leave us with x squared. Negative 6x divided by 3 will give us negative 2x. And then we'll just leave this as a positive 2/3. And 0 divided by 3 is just 0. Now we've fixed our trinomial. Now the coefficient of the x squared is a 1, so now we'll be able to use those tricks. Step number 3, let's start by copying down where we left off. Now our ultimate goal when we're completing the square is to create a perfect square trinomial. This is not a perfect square trinomial, because if you take this number here, negative 2, divide it by 2 and square it, you do not get 2/3. So this is not a perfect square trinomial. So we want to create a perfect square trinomial. So the first step of that process is we got to get rid of this constant. We're going to move it to the other side. So let's subtract 2/3 and subtract 2/3. That will leave us with x squared minus 2x. These cancel, so we're just left with negative 2/3. And then we're going to write these orange boxes to help us remember that we need to fill in those spaces in step number 4. Next step, I'm just going to copy exactly where we left off with down here. Okay, now remember, our goal is to turn this into a perfect square trinomial. And how do we do that? We use our special trick, and the special trick says take the coefficient of the x, which in this case is -2, divide it by 2 and square it. And let's see, -2 divided by 2 gives us -1, -1 squared gives us a +1. This is what we're going to insert into these two boxes. So we're going to put a +1 here in order to create our perfect square trinomial. This is a perfect square trinomial because this number divided by 2 and squared it gives us our constant. And then if we add 1 to the left side, we have to also add 1 to the right side. Now let's just simplify this on the next line. I'm going to start by copying down this perfect square trinomial. So we've got x squared minus 2x plus 1. And then let's just go ahead and take -2/3 plus 1. And you can either do that by hand or punch it into your calculator. Either way, -2/3 plus 1 will give us 1/3. And again, let's fill in this instruction box here. We took the middle coefficient, which is often called b, we divided it by 2 and squared it, and that told us what to put in this orange box here. Now, we've created a perfect square trinomial. So the next step is to factor that perfect square trinomial, and we know any perfect square trinomial will factor perfectly as some quantity squared. So to start off, I'm just going to copy this exact expression down into the box for step number 5. So again, this is the perfect square trinomial that we've created. Now we're going to factor it. Now let's use our shortcut. We know that this is a perfect square trinomial, so we know it'll factor, and it will look like this, and we can even put an x there. Then to figure out what to put here, we can again use that middle coefficient, the -2, and we take -2 and divide it by 2. Don't square it in step number 5. In step number 5, just take it and divide by 2. And -2 divided by 2 gives us a -1. So that's what we're going to put right here, -1. Now we've factored our perfect square trinomial. Next, I'm just going to copy this exact expression over into our box for step number 6. And now for step number 6. We've now rewritten our problem in a way that we can now apply the square root property. And since the squared term is already isolated, we can just go right ahead and take the square root of both sides. And let's make sure not to forget the plus or minus. The square root of x minus 1 squared leaves us with x minus 1. To simplify this, let's use the quotient property of radicals, which says we can break this apart into 2 separate radicals. So we'll rewrite this as plus or minus the square root of 1 divided by the square root of 3. The square root of 1 is just 1, so let's go ahead and replace the square root of 1 with 1. Now we're almost there, but we do not like to have radicals in our denominator for our final answer. So we need to rationalize this denominator. In other words, we need to get rid of that square root in the denominator. To do that, let's multiply the top and the bottom of this fraction by the square root of 3. And let's see what that leaves us with. We'll bring down the x minus 1, plus or minus. 1 times the square root of 3 leaves us with the square root of 3, and the square root of 3 times the square root of 3 just leaves us with 3. Now, when a problem asks you to solve, that means for our final answer we should have x isolated. So to isolate x, let's add 1 to this side and add 1 to the other side. And then for our final answer, on the left side, we'll just be left with x. On the right side, we could write our answer as plus or minus radical 3 over 3 plus 1, but it's more common to write the 1 first, and then this big plus or minus radical piece last. So we'll put plus or minus square root of 3 over 3. And this is our final, fully simplified answer. The last 2 problems, problems 10 and 11, are just extra practice for completing the square. So you can go ahead and try those problems on your own. I'll post the worked out solutions, but you can also see the final solutions here.